In today's world, we often use things that get very hot for simple things such as cooking on our stove or in our oven, to maybe a step further of protecting us from a little bit of fire, like such. The question is, do these technologies really cook the way we want them to cook, or protect us the way we want to be protected? And today, we're going to be stress testing these situations to find out. Our setup is simple, just a thermoresistor attached to our microcontroller Arduino, ready to take data and be sacrificed if needed.
This is our Arduino code. In the setup function, the pins connected to the input-output connection on the SD card is activated, and the file that will be used to store our data is clear. In the loop function, the time variable is updated, and the voltage received from the thermoresistor is converted into a temperature in degrees. Then the file to write to is opened, and a line of text is written to the file for later analysis. Lastly, the loop waits for half a second before repeating to avoid any potential problems with overloading the Arduino. This is a picture of the experiment when the thermoresistor is inside the oven and the Arduino is taking data. Looking closely at the oven's temperature when it was set to 300 degrees from room temperature, it rose in an almost linear fashion, heating up at just over a degree per second. When the oven was turned off, the temperature followed an exponential decay with two sets of parameters. In the first experiment, the thermoresistor was placed in the middle of an oven and the temperature was increased at 15-minute intervals. The black line shows the temperature the oven should be reading if it was perfect. The oven always overshoots the expected temperature, then dies off gradually. In the next trial, the same setup was used and the temperature was set to 300 degrees Fahrenheit for 50 minutes, then the oven was turned off. The temperature was initially overshot, but the oven's internal thermometer would turn back on after the temperature reached about 245 degrees.
The next thing we wanted to test was the effectiveness of hydrogel or sodium polyacrylate. Using the fire retardant glove and a layer of the hydrogel, we wanted to see how much temperature was resisting from within the glove. Sodium polyacrylate is a superabsorbent polymer that can be used to stop anything from getting warm if applied correctly. By absorbing up to 800 times its own weight in water, the gel will burn off layer by layer before anything underneath it gets heated up. Because it won't burn, a layer of sterno is applied directly above the hydrogel. A successful trial shows that even after 45 seconds of being on fire before the sterno extinguished, the maximum temperature reached was only about 70 degrees. This includes a 20-second period of virtually no temperature increase. In this trial, no gel was applied after the previous test to see what residue was left. In a matter of milliseconds, the thermoresistor had reached its peak voltage. Without a doubt, the sodium polyacrylate had protected the sensor from a significant amount of damage and could do so for other uses. From the study on thermal stability of thermosensitive hydrogel, we look at their data when it comes to dealing with superabsorbent polymers. Although they use different polymers, they do reach the same conclusion that superabsorbent polymers have a super high thermal stability and excellent flame retardant effects. At the end of the day, we believe our experiment was successful and our results were both practical and useful.